All right, class, this is Unit 2. This is the third video. We're starting at the bottom of page 3, and we're going to discuss the SI system. So the SI system, or what's the international system, is the most recent adaptation of what we call in the United States the metric system. The system was adopted to ensure standard measurement within the sciences. The SI system is used throughout most of the world, and the notable exception is the United States, where most of us use the imperial system, such as miles and pounds and gallons on a daily basis. The biggest advantage to the SI system is that conversions are based on multiples of 10. So here I have a table, and we're talking about multiples of 10. This is how they work within the SI system. We have prefixes that tell us how large or how small our particular number is. And then there's an abbreviation symbol. There is a multiplier, which this is how big it is in standard notation, and this is in terms of powers of 10. So we're going to go through these one at a time. The first one that I have on the list, and there are larger things than giga. Giga. Symbol is G. The multiplier is 10 to the 9th, or 1 billion. Giga is pretty commonly used these days because most of us have a data plan for our phones, and they are in terms of gigabytes, or in terms of bytes times 10 to the 9th power. So a very large number of bytes. Then we have mega, also frequently used in terms of data, and that one symbol is capital M. This one, the multiplier is 1 million, which is 10 to the 6th power. If you remember the things on this chart, this can make scientific notation a little bit easier because you have a pretty good idea of the powers of 10. Kilo or kilo. This one is also pretty large. You'll see these. Kilobytes is one of them, although it's kind of outdated because most things don't run in terms of kilobytes anymore. Most things are in terms of megabytes and gigabytes. There's also kilograms, and this one, the symbol is a lowercase k. It means 1,000, or 10 to the 3rd power. Kilograms, kilometers both fall into these. Kilograms is 1,000 grams. Kilometers is 1,000 meters. Then we have centi. This is a lowercase c. It is 10 to the negative 2nd, or 1/100th. Cent comes from this. Divisions of 100 is what we're talking about here. Next up is milli. The abbreviation for this one is a lowercase m. It is a multiplier of 1/1000th, or 10 to the minus 3rd. So there are two frequently used units in terms of milli in a chemistry classroom. You could be talking about milliliters. There are 1,000 milliliters in 1 liter. Another possibility is millimeters. So if you have a meter stick and you look at it, you'll notice there are some lines that are very close together, and there are 1,000 of them. There are 1,000 millimeters in 1 meter. Next up is micro, and the symbol for this is a Greek letter, and it looks kind of like this. It's like a U with an extra tail on the front, or an M that's very pointy on the top. This is its name. It's a mu. This is micro. This is 10 to the negative 6th power. Then we have nano. That's a lowercase n. You'll hear this like nanotechnology or nanometers in terms of light. And this is going to be times 10 to the negative 9th power. Pico, lowercase p, this is times 10 to the minus 12th. Femto, lowercase f, times 10 to the negative 15th. We will see every once in a while femto show up in chemistry because the distance between atoms is often in the range of femtometers, or 10 to the negative 15th meters. We will use the international system in this class. After this chapter, we're not going to use the imperial system. Since most of us are unfamiliar with the metric system, we need to define the various units. So for time, the unit is the second, abbreviated with a lowercase s. Specifically, the time is measured in seconds. We're not talking about hours. We're not talking about minutes. We only use seconds. So if I were going to talk about a period of 10 minutes, I would say 600 seconds. The original determinations are over here. So originally, somehow they divided it up into 86,400 pieces of a day. The current one is based on the cesium-133 atom, and they measure its vibrations as it just sits there. And this is what's known as the atomic clock. You can look into that if you're interested. Atomic time is very accurate. It loses only seconds per millennia. For length, the SI unit is the meter. It is a lowercase m. So originally, it was considered 10 to the negative 7th, the distance from the equator to the North Pole, and I'm not sure how they measured that. Nowadays, they measure the distance light can travel in a vacuum in 3 times 10 to the negative 8 seconds. The speed of light itself is 3 times 10 to the 8th meters per second. Temperature. You would be tempted to think that this is going to be Celsius, but Celsius does not quite do what we want in chemistry. So we are using Kelvin. It is a capital K for the abbreviation. It's based on water, but it's mostly based on absolute zero. A temperature of 0 Kelvin is absolute zero. It is the coldest possible temperature in the universe, and more accurately, it's the coldest theoretical temperature because we have never actually measured anything with a temperature of 0 Kelvin. We have come close. There are laboratories on the planet that can get very close to zero, but they've never actually hit zero. These days, they have reworked it. It's based on a physics constant that we're not going to really discuss that much. The amount of a substance, so we're talking about how much of a chemical, is in terms of moles. And the abbreviation for this is MOL, moles. The basis for this is the number of atoms in 12.0 grams of the carbon-12 isotope, something that we'll get more into in later units. This is an exact number of particles. This is the number 6.022 and so on times 10 to the 23rd, which we would abbreviate to 3 significant figures. We'll talk about significant figures later in this unit. So 3 digits, 6.02 times 10 to the 23rd. This is a very large number. And the important thing about this number is that we can classify the amount of a substance in relatively tame numbers, even when there's a huge amount of particles. So if there was 7 times 10 to the 23rd number of carbon atoms, it would be easier for us to just say that there's about 1 point something moles. It makes it a lot easier to discuss the amount of a substance. The last one in this table is mass. And the base unit of mass, interestingly enough, is the kilogram, which is kg. A kilogram is 1,000 grams. So we would think that the gram is the base unit, but it's actually not. And the reason for this is over the last couple hundred years, we have had this specific object that serves as, it serves as the prototype for this. So anytime we need to know exactly 1 kilogram, we would get out a prototype and we would compare them. And that's how we could get these two to work together. Originally, it was based on this piece of metal in France called Le Grand Quai. It is in a very secure vault. So you would travel down an elevator and it's in a secured room that only about 3 people in the world can access. And this piece of metal is under a jar and vacuum sealed. Then they put another jar on top of it and vacuum seal it. They are very protective of this piece of metal. Now, in the last couple of years, I want to say it was 2018, they changed it. It is no longer based on this piece of metal. They still have it, and it's still significant, but they have changed the definition of the kilogram, and now it's based on something called Planck's constant. And that's another of our complex physics things that we will not discuss in this class.